Hello, hello. Going to be looking at the Architect Studio Companion. This is the 5th edition. Specifically today, we're going to be taking a look at some of the mechanical systems and even some electrical systems. Hopefully get through this somewhat quickly. It's kind of a big chapter, so I'll try to go through it kind of as efficiently as possible. This time looking at Section 4, Designing Spaces for Mechanical and Electrical Services, a big one that is covered in the NCARB testing, and that should just kind of be known, should just be well known in architecture as well as contracting. So let's go ahead and get to it. Designing spaces for mechanical and electrical services. Just as a primer, this is going to be a lot of kind of reading off the page with some interpretations herein. Constant air volume, CAV system. So the short of this one really is that you have an air handling unit in the basement or sometimes on the roof that is fed by the refrigeration machines, the refrigerant providers, the boiler or the chilled water plant. And this one air handling unit provides a constant volume of air throughout the served units, throughout the served spaces. Right? This is kind of the most simple and straightforward all air system available. So going through the text here. Air conditioned mixed with a percentage of outdoor air, filtered, heated or cooled, and humidified or dehumidified at a central source. Supply and return fans circulate the air through ducts in the occupied spaces of the building. A master thermostat controls the central heating and cooling coils to regulate the temperature of the building. Right? So oftentimes the facilities manager will have total control over the thermostat in the space. Or you'll see this sometimes in a single-family residential house, where one thermostat sets the temperature for the entire space. Typical applications: spaces that have large open areas, so perhaps a one-room movie theater. Actually, a one-room movie theater will often have one for the actual theater space and another zone for the concessions, entry, bathrooms. So spaces that have large open areas, few windows, and uniform loads, such as lobbies, department stores, theaters, auditoriums, and exhibition halls. The advantages of this system is that it offers a high degree of control of air quality, right? So as mentioned before, you could do you could filter the air, mix it in with outdoor air or room air, humidify, dehumidify. It is comparatively simple and easy to maintain, right? So if someone needs to fix anything in the air handling unit, someone can just come into the basement or on the roof and fix it there without having to disturb any of the occupied spaces. The disadvantage is that the entire area is served by the system in a single zone with no possibility for individual temperature control, right? So these people have the same quality of air, temperature of air as the people here, whether this person needs heating or cooling and this one needs the opposite. There's no say in the matter. The major components are boilers with the chimney, chilled water plant with the cooling tower above, fan room, which is here, outdoor fresh air and exhaust louvers, vertical supply and return ducts, horizontal supply and return ducts, supply diffusers, and return grills. Alternatively, in buildings of moderate size, a packaged system may be used in place of all components other than duct. So for a packaged unit, oftentimes you'll have the air handling unit, which is this, on the roof, and it'll be everything. It'll be the boiler, the chilled water plant, and the air handling unit, and it has the ducts serving each space, and oftentimes sometimes the exhaust, the return ductwork, the exhaust ductwork will just be like that, blowing air out into the outside. Alternative buildings, the single package system incorporating all central components in a single metal box may be installed on the roof or outside on an exterior wall, or a split package system may be installed with a compressor and a condensing unit in an outdoor box and an air handling unit in an indoor box. So these are very common, again, in single family residences, certainly in Miami, where you have kind of a big box just outside on the exterior wall with a large condenser that's blowing hot air out into the outdoor space. Sizing the components. For the dimensions of these components, okay, see the charts on pages, blah, blah, blah. So kind of continuing along the variations of the CAV, a furnace is an indoor unit that incorporates a source of heat and an air circulating fan into a single metal box. The source of heat may be a gas burner, an oil burner, an electric resistance coil, or a heat pump coil. Cooling coils may be also incorporated if desired. The capacity of furnaces is limited to such an extent that they are used most in a single-family house and other very small buildings, as we mentioned earlier. Multiple furnaces are sometimes used to heat and cool somewhat larger buildings. A single duct constant air volume reheat system is identical to the CAV up to the point at which the air enters the local ductwork for each zone. In reheat systems, the air then passes through a reheat coil. The reheat coil may carry hot water or steam piped from the boiler room, or it could be an electric resistance coil. A local thermostat controls the temperature of the reheat, allowing for close individual control of room temperature. Reheat systems are typically used in situations requiring precise temperature control and constant airflow, such as a laboratory, a hospital, operating room, or specialized industrial spaces. Because CAV reheat systems are inherently wasteful of energy, first cooling air and then reheating it, they are often not specified for new buildings. In the multi-zone system, several ducts from a central fan serve several zones. In one type of multi-zone system, dampers blend hot and cold air at the fan to send air into each duct at the temperature requested by the thermostat in the zone. In another type, reheat coils in the fan room regulate the temperature of the air supplied to each zone. Multi-zone systems require a large amount of space for ductwork in the vicinity of the fan, so they are generally restricted to small number of zones with short runs of ductwork. Packaged multi-zone units are also available. So here we have kind of the system. This is a multi-zone system where you have the same as above, right? The fan room pumping chilled water or boilers through it. Hot outdoor and recirculated air comes through. But in this system, you have you have 3 zones. And so this is really just the same flavor as above, except you get more thermal control in the different zones because you've just multiplied the amount of ducts running through the system. So it's kind of cumbersome, right? In that you need a lot more space for ductwork, but you do get the added advantage of the zones, local thermal control. Another central all-air system, the single duct variable air volume, shorthand VAV, is illustrated here. The Cliff Notes version, the short version of this, is that it's quite similar to the CAV system, except for this one element, which is the VAV box, where in each thermal zone you have a thermostat, similar to how we saw with the multi-zone system CAV, except here the control is occurring in the VAV terminal box within the space. So again, the shorthand of this really is that this is the same as CAV, except that a damper, a flap, for all intents and purposes, within the space closes or opens the amount of air coming in. So you can have a lot, if cool air is being produced in the air handling unit and is being piped into every zone, then you can control the amount of cool coming into the room by just, if you want it less cool, you close the damper. If you want it more cool, you open it. It's really quite that simple. Reading herein, air is controlled, mixed with a percentage of outdoor air, filtered, heated, or cooled, and humidified or dehumidified, at the central source. Supply and return fans circulate the conditioned air through the ducts to the occupied spaces of the building. At each zone, a thermostat controls room temperature by regulating the volume of air that is discharged through the diffusers in that zone, right? Simple as that. Typical applications: VAV is the most versatile and most widely used system for heating and cooling large buildings. That's important to note. The advantages are that it offers a high degree of local temperature control at a moderate cost. It is economical to operate and virtually self-balancing system. Unfortunately, VAV is limited in the range of heating or cooling demand that may be accomplished within a single system. When one area of a building needs heating and another needs cooling, a VAV system cannot serve both areas without help from a secondary system. So a secondary system example, and it might be covered later, but I'll just address it here, is a VAV system with terminal reheat. So that's just the same system that we've just been looking at, except here, well, here or here, there might be a heating coil. Maybe it's electric, maybe it's a refrigerant pipe that just creates a hot coil here, and the cold air coming through here hits the heating element, and then you have slightly warmer air or much warmer air coming out into the space. Now, it's technically quite inefficient to be doing that, right? If you have cool coming here and then you're just cooling air in order to heat it up again, it's obvious that that's really not that efficient. Moving right along. The major components are boilers and chimney, chilled water plant, and the cooling tower above to cool the hot water. To cool the hot refrigerant. Fan room, outdoor fresh air and exhaust louvers, vertical supply and return ducts, horizontal supply and return ducts. So this right here is the example of the single duct variable air volume system. Continuing with the descriptive text here. Alternately, in buildings of moderate size, a package system may be used in place of all components other than ducts. VAV control boxes, diffusers, and grills. A single package system incorporating all central components in a single metal box may be installed on the roof. So this is similar to the CAV system, right? It's that this air handling unit down in the basement could often be up here with all of the elements within it, and the ducts kind of come here, exhaust from each space. The VAV control box is usually concealed above a suspended ceiling. It is approximately 8 to 11 inches high for zones up to 1,500 square feet in area, and up to 18 inches high for zones up to 7,000 square feet. Its horizontal dimensions may vary with its capacity up to a maximum length of about 5 feet. To size the other components of the VAV system, use the charts ahead. So going to the variations, in buildings with large areas of windows, VAV is often combined with a second system around the perimeter of the building to deal with large differences in heat and cooling demand between interior and perimeter rooms. The second system is most commonly either an induction system or hydronic convectors. So the hydronic convectors are just the hot pipe perimeter system that you see in kind of old buildings sometimes. A single duct VAV reheat system, as mentioned before, is identical to the basic VAV system up to the point at which the air enters the local ductwork for each zone. In a reheat system, the air then passes through a reheat coil. All of this I mentioned before, but I'll just go over it. Before it is distributed to the local diffusers. The reheat coils may be either an electric resistance coil or a pipe coil that carries hot water circulated from the boiler room. A local thermostat controls the flow of water or electricity through a reheat coil, allowing for close individual control of room temperature. This variation can overcome the inability of a VAV system to cope with wide range of heating and cooling demands. VAV reheat systems are more energy efficient than constant air volume reheat systems because in the VAV systems, the reheat coil is not activated unless the VAV system is incapable of meeting the local requirements for temperature control, and a much smaller amount of tempered air is circulated. In the VAV induction system, a smaller volume of conditioned air is circulated through a small, high-velocity duct from central source. Each outlet is designed so that the air discharging from the duct continually pulls air from the room into the outlet, mixes it with air from the duct, and discharges the mixture into the room. This variation is used where limited space is available for ducts. It is also used to maintain a sufficient level of air movement in spaces that do not have high demand for heating or cooling. In a dual duct VAV system, paired side-by-side ducts carry both heated and cooled air to each zone in the building. At each zone, the two air streams are proportionate and mixed under thermostatic control to achieve the desired room temperature. This variation gives excellent local control, temperature control, but it requires an expensive and space-consuming duct system, and it is not energy efficient. Looking now at fan coil terminals, another very popular system. So in short, the fan coil box, sometimes it's in a concealed, in a drop ceiling above, but oftentimes you'll see it like this as a kind of a box unit at the perimeter of an occupied space. Air comes in from the bottom here and discharges above as conditioned air. Just go through this. Hot and or chilled water are piped to fan coil terminals within the space shown here. At each terminal, a fan draws a mixture of room air and outdoor air through a filter and blows it across the coil of a heated or chilled water and then back into the room. A thermostat controls the flow of hot and chilled water to the fan coils to control the room temperature. Condensate that drips from the chilled water coils is caught in a pan and removed through a system of drainage piping. In most installations, the additional volume of air brought from the outdoors is used to pressurize the building to prevent infiltration or is exhausted through toilet exhaust vents. So it's important to kind of get some amount of fresh air into the space so that, here just to kind of illustrate the point here, if you have a negatively pressurized building, it's like the walls are kind of being sucked in. You don't want that, because what happens is that air from outside comes in and you get pollutants from outside. You get the assembly of the envelope suffers. You're likely to get kind of moldy insulation just because basically air is being sucked in from the outside. You always want a positively pressurized space, slightly more pressurized than the outdoor air. So this outdoor air coming into the fan coil units helps with exactly that. Typical applications for an FCU fan coil unit: buildings with many zones, such as you have here. You have 1, 2, and 3, all located on exterior walls, such as schools, hotels, motels, apartments, and office. Right? It's important to have exterior walls so that you can get exterior air input. The advantages are that no fan rooms or ductwork spaces are required in the building. The temperature of each space is individually controlled. Now, this is true for certainly this schematic that we see here. Sometimes you'll have a condition where the fan coil terminals in each room, yes, are only fed by chilled water and hot water, but sometimes what can often happen, or what can often be the case, is that you have a smaller network of ductwork, much smaller than you would need for a CAV or VAV system, that would pipe in fresh air into the fan coil terminal, fan coil unit, such as this. But again, since it's a kind of a more localized system, these can be, there's no, these can be about half, maybe sometimes less, depending on the system, the requirements of the system. The disadvantages of FCUs is that humidity cannot be closely controlled. The system requires a considerable maintenance, most of which must take place in the occupied space of the building, right? If this is a bedroom, for instance, a maintenance person needs to come in and do the work directly in the occupied space. The major components are the boilers, chimney, chilled water plant, cooling tower, same as kind of what we saw with the CAV and VAV, vertical supply return piping, horizontal supply and return piping, condensate drainage piping. So all that the condensate drain pipe really is, it's just because water will often drip off of the pipes, the condenser pipes. You just need a way to kind of get that out of the space. You don't want mold. You don't want any kind of bacterial growth to result from condensate. That's often how you get Legionnaire's disease, which was an issue in New York a couple of years ago. I think it was roughly 2005 or so, 2010 maybe. Sizing the components. Fan coil terminals are usually sized to fit beneath a window. Heights range from 25 to 28 inches in depth, from 9 to 12 inches. and lengths from 30 to 84 inches. For the dimensions of the other components of the system, look ahead. Variations on fan coil terminals are also manufactured in horizontal ceiling, as mentioned earlier, ceiling hung configurations, and in tall, slender configurations like in a closet for mounting vertical chases. Another central all-water system is the closed-loop heat pump. The closed-loop heat pump is a water-to-air heat pump A central all-water system shown here is the closed-loop heat pump. A water-to-air heat pump unit in each space provides hot, cold, and fresh air. The water source for all the heat pumps in the building circulates in a closed loop of piping. Control valves allow the water source to circulate through a cooling tower in the summer and a boiler in the winter, and to bypass both the boiler and the cooling tower in the spring and fall, and at other times when the heating and cooling needs of the various rooms in the building balance one another. So yeah, the shorthand of this is called the heat pump system, and it's great for climates where, like temperate climates, such as anywhere between, let's say, Virginia and upstate New York, for instance, where summers are hot, the winters are cold, and spring and autumn are typically quite mild, and so you can kind of reverse the typical refrigerant system so that what was doing cooling in the summer is doing heating in the winter. The typical applications for a heat pump is hotels containing chronically overheated spaces like kitchens, laundry, assembly room, and restaurants. And the good things about this system are that it's an efficient system in which heat is extracted from chronically overheated spaces, like we talked about earlier. Can be used to heat underheated areas. So heat is pulled from overheated spaces like a kitchen and can be delivered to a cold space. For instance, so this can be like in the fall in a hotel. If the kitchen is very hot, you can pull the heat from it and serve a bedroom space that has a thermostat set to require heat. The disadvantages, however, is that it's an expensive system to install, and careful economic analysis is needed to determine if the high installation cost can be balanced by the energy savings. The heat pumps require that much of the routine maintenance take place in the occupied space. So again, using kind of the hotel example, the maintenance person would have to go into the occupied space to fix the system. The major components, as you can see, are the heat pump unit, the boiler room, the cooling tower, as well as the chimney. Sizing the components. The heat pumps may be located above a drop ceiling, over a bathroom and dressing area in a hotel room, or below windows. A typical under-window heat pump unit is approximately 30 high, 12 deep, and 60 inches long. An above-ceiling unit has approximately the same dimensions, with a 12-inch dimension vertical. For the dimensions of the other components, see ahead in the charts on page 210 to 211. So you can tell here it looks very similar to the FCU, to the fan coil unit, right? This is the thing in the back. Taking a look at another all-water system is the Hydronic Convector, which is a popular system when all you really need is heating, or if you have another way of getting cooling into the space. Hot water from the boiler room is circulated through fin tube convectors, which are horizontal pipes with closely spaced vertical fins, here shown as baseboard units, usually mounted in a simple metal enclosure with an air inlet opening below and outlet louvers above. So just to kind of skip ahead, this is what they look like in the space, and surely you've seen these if you've been anywhere in a cold climate, often as baseboards. The heated fins, working by convection, draw cool air from the room inside and from the enclosure below, heat it, and discharge it out the top. Typical applications. Hydronic convectors are used alone in buildings where cooling is not required and where ventilation may be accomplished by opening a window or through a supplemental ventilation system. They are also used as supplemental source of heat in combination with other heating and cooling systems. The advantages of this system really is that it's an economical system to install and operate. It provides excellent comfort during the heating season. Convectors are available in very many different kinds of configurations and designs. Local control of temperature is possible through thermostatically controlled zone pumps or zone valves, through self-contained thermostatically controlled valves at each convector, or in some types of convectors, usually through manually controlled dampers. The disadvantages are, again, that it's really for heating only. Cooling, humidity control, and ventilation has to be done separately. The major components are really simple: boilers, chimneys, the chimney serving the boiler, vertical supply, and return piping for the heating elements. Sizing the components. Hydronic convectors usually run continuously around the perimeter of a building. Each convector contains one or sometimes two continuous fin tubes. The sheet metal enclosures for the fin tubes are available in a variety of configurations. The smallest is only about 5 inches square in cross-section and should be mounted at least 4 inches above the floor. Enclosures of up to 28 inches high and 6 inches deep are often used for improved thermal performance. The top of the enclosure contains small louvers and may be sloping or flat. Variations. Hydronic heating is useful in buildings down to the scale of single-family residences. In spaces where insufficient perimeter is available for convectors or where the presence of convectors is undesirable, fan-forced unit heaters may be used. These are housed in metal cabinets that may be recessed in a wall, mounted on the surface of a wall, or even suspended from the ceiling structure. Each heater contains a hot water coil fed from the boiler room and an electric fan to circulate air across the coil. Unit heaters are very compact in relation to their heating capacity compared to convectors. The last one to look at here as a local system is the package terminal unit and through-wall unit. The description here reads, one or several through-the-wall units or package terminal units are mounted on the exterior wall of each room. So these you'll see often. These you'd see in a hotel or motel as just kind of a big box stuck into the exterior wall, or the through the wall unit, and the simplest version of this really you'll see kind of in a New York City apartment where it's just a window unit is similar to what we're seeing here. Within each unit, an electric powered compressor and evaporator coil provide cooling capability. Heating is supplied either by electric resistance coil or by utilizing the compressor in a reversible cycle as a heat pump. A fan draws indoor air through a filter, adds a portion of outdoor air, passes the air across the cooling and heating coils, and blows it back into the room. Another fan circulates outdoor air independently through the unit to cool the condensing coils. A control thermostat is built into each unit. So in this case, sometimes here or anywhere on the unit is where you would go to adjust. Sometimes also the new ones have a remote control, like a television, where you could adjust it from the bed or from your desk. There are several alternative types of equipment that fit into this category. Package terminal units, also called PTACs, package terminal air conditioning, are contained primarily in an indoor metal cabinet that fits beneath a window, like I mentioned in a motel. They are connected to outdoor air with a wall box and an outdoor grill. Through-the-wall units are contained in a rectangular metal box that is mounted directly in an opening in the exterior wall of the building. A variation on the through-the-wall unit is the familiar window-mounted unit that I mentioned earlier, used only for low-cost retrofitting of existing buildings. The only service distribution of any of these types of units is an electric cable or conduit. So again, as I mentioned with the window unit, something like this, all it really requires is for you to be able to plug this into the wall. The typical applications are apartments, dormitories, motels, hotels, office buildings, and nursing homes. The good things about this system are that it's readily available and easily installed. Install costs are often lower than those for central systems. Each room has individual control of temperature, really important. No building space is utilized for central equipment, ductwork, or piping, right? So it's kind of an all-in-one system right there in the room. Operating costs may be lower than those for central systems in buildings in which not all spaces need to be heated or cooled at the same time. Cooled all the time, such as motels. Disadvantages, however, maintenance costs are high and equipment life is relatively short. Maintenance must be carried out in the occupied spaces. The equipment is often noisy and inefficient. Air distribution can be uneven. Wintertime humidification is not possible, and operating costs are high in areas with very cold winters and costly electricity. Through-the-wall and window-mounted units can be unsightly, right? So often you've seen in the exterior of any in Chicago or New York, you see a building that's every window during summer. Every window has a kind of an ugly, and they're not even all the same kind, window air conditioning unit. Sometimes it's not that ugly, but oftentimes it's just, if it's a well-designed building, if you have to have a window unit in each one, it's kind of not great looking. Major components really are just the package terminal unit or through-the-wall unit, and the typical dimensions are given in the tables provided.